they start campaigning, while I'm driving, I'm going to get upset.
Yeah, you are not supposed to vote while driving. I mean, it broadcasts pre-recorded votes.
Right.
But your kids in the back can vote. I mean, nobody can stop them.
Mm-hmm.
But obviously, the driver shouldn't. He shouldn't see the screen, right?
Theoretically.
At least in California.
Right, yeah, I think it's not a good idea.
So in our experiments, we didn't vote like driving with the system.
Were you really driving?
Yeah.
No, okay.
Yeah, we don't have a good quality simulator, so we had to do real tests.
It's better.
I mean, simulators could do it if you have the money, but they're expensive. Students are cheaper.
My graphics aren't nearly as impressive as that last talk. I don't have any mathematical formulas either. So, it's time to start this one. So I'm Justin Rohr from the Naval Postgraduate School, and this is an architectural paper on creating DTN hybrid networks for vehicular communications. So this is a system that colleague Jeff Shea and I have been working on for a while, along with a few of our students. For those that don't know where Monterey is, it's about an hour and a half south of San Francisco on the Central Coast. It's a pretty place to visit, so if you haven't been there, I recommend it. The goal of this architecture is to provide a converged IP and DTN capability, kind of taking the best of both worlds. And benefits to that are minimizing the effects of link disruptions and outages, but using the basic IP structure when possible to minimize overhead. And we're trying to do this in a software solution that can either operate in a standalone device, like a router network, or be integrated into an end system, like a smartphone or an embedded platform vehicle. And one of the main goals here is not requiring any change of the end user applications, so being able to take advantage of the whole ecosystem of IP applications that already exist. And to do that, we're using open source software as much as possible. So to kind of visualize this scenario, you have your connected traditional IP infrastructure on the left, where there's cell phone towers or what have you that that people and vehicles connect to reach the rest of the world. And then when you get into more rural, less well-connected areas, you get out of the range of these infrastructure installations, and you would like to be able to connect through the vehicles and devices around you and reach back to the rest of the world if possible. So with traditional IP infrastructure only, that's rather difficult to do because of the challenges present in the disrupted wireless environments. So that's my name. So a little background on DTN itself. Disruption-tolerant networks are designed to deal with scenarios of high mobility, which we have in digital networks. In the best case, high mobility just causes frequent routing updates and changes, which is a challenge in limited bandwidth wireless deployments. It's also likely that you see sudden partitions form the network. And in the worst case, you never have coherent end-to-end paths where you can send and receive packets at one time. They have to go through some sort of hop-by-hop networks can run into some or all of these constraints. Some of the approaches that have been developed so far are modifications to TCP, so that's kind of the least invasive because TCP is well understood at the application layer. However, that only gets you so far. You can't deal with the lack of coherent end-to-end paths just by modifying TCP. There's some domain-specific non-IP approaches to specific types of networks, and that's nice because you can heavily optimize it for your environment. However, you lose the whole ecosystem of IP applications that exist. And then you have the DTN bundling protocols, which is the approach that we're looking at here. This was developed originally for interplanetary networks and extended to other types of networks. And it has a reasonable amount of development and design behind it. We've been around since the 90s, I guess. And there's a number of different implementations that are interoperable and form an application overlay that can run on kind of customized link layers or on standard IP stack, and have a number of DTN-specific routing protocols that have been developed to accommodate some of the challenges in highly mobile environments. The downside is that it also requires customized applications, so this doesn't support natively IP applications. So the places where this has been used is things like deep space probes or satellites or the space shuttle or the International Space Station, where they're writing custom applications to work with this protocol suite, and they're okay with that requirement. So our challenge was to see if we could get the benefits of the DTN bundling protocols and make it work with traditional IP applications. So we call that the IP come DTN architecture, basically because it sounded more sophisticated than saying IP and DTN together. From the high-level view, this is what our architecture looks like. So you have, and this would be for the standalone version. So you have a device with a number of interfaces like a router, traditional IP network layer, DTN bundling agent runs on top of that, and our piece of software runs alongside that, and it communicates both with the IP networking, the routing that's happening there, as well as the DTN agent. So as far as the DTN bundling protocol is concerned, our software looks like a DTN application. So essentially, at least in the original version of this, we let the IP layer do its thing. As long as IP routing is working normally, so your infrastructure, you have strong connected paths, let it do its thing, and don't add the additional overhead that DTN introduces. But once that breaks down, our software would take over and start storing and forwarding the IP packets through the DTN network. So that is implemented as a multi-threaded DTN application with a number of components that I won't spend too much time on, but essentially a packet reader that reads packets from the kernel, buffers them, and a module that takes those and writes them out to DTN bundles and aggregates multiple packets into a single bundle to decrease the overhead of the DTN header. And then on the reverse side, those packets can be read back out of the bundles when they're received and written back out to the network as traditional IP packets. And there's a management thread that keeps track of what's happening and kind of synchronizes the IP routing with the DTN routing, which are two fairly different processes. And we're currently on the second generation development of this system. So, 2 slides ago, we had that one block, which is our software. We expand that out. That is the IPCOM DTN software block. So that communicates with the external DTN bundling protocol, of which there are a couple in existence to choose from, and traditional socket interfaces. We have a number of modules taking in packets and producing bundles, and on the reverse side, taking bundles and producing packets. And a decision plane that looks at what packets should be bundled and where should they be sent. So on the IP side, we've been using OSPF for routing because it's nice and fast. It will tell us very quickly if the traditional IP route fails, which point our software can take over. And then we have the potential to use a variety of DTN routing protocols, which is kind of future research. At this point, we're using the epidemic. We're not really looking at the heavily loading the network. But because the bundling protocols are modular, we can swap out routing protocols later on and get what performs the best. So, we've talked about kind of the mechanics of this, but the big question is how do you do this in a way that doesn't break your existing IP applications? Because of course they're not designed to operate with a disrupted network. So, fundamentally, applications have different levels of disruption tolerance. So if you're talking about voice over IP, that's a real-time application. I'm talking about a specific software package, but voice over IP in general, you're talking about a real-time interaction. You have like a 200 millisecond threshold beyond which that data is not useful anymore. So it doesn't make sense to bundle this and keep it around and send it later when it's not going to be useful on the receiver side. So we would probably drop that traffic. On the other hand, you have applications like chat. Chat, you probably don't care if your message arrives in 1 millisecond or 500 milliseconds or 3 seconds. Right? That's not a real concern at the user level. You probably care whether they arrive in the right order, but the speed is not as critical. So chat fundamentally can tolerate some delay, but a lot of times chat is implemented on top of TCP, which times out or breaks down when you have a disrupted network. So in our case, we would have a module that handled that application and can essentially split the TCP connection and keep TCP alive and bundle those chat messages to be delivered a little bit later. In one case, we were doing this with the SIP protocol, which is actually on top of UDP, but we were able to not only bundle the messages to be delivered later, but actually notify the user by injecting a return SIP message that said your message has been delayed, but it's not lost. So our premise is that the network should be, or the gateway should be aware of these different needs of the applications and handle them adaptively and transparently. And also that the architecture should be modular and composable, because obviously our little research group is not going to write a module for every single application in the world. We're doing some kind of common high-value modules and providing templates so that others can also contribute modules to the software architecture. So essentially we do this via application profiling. So we look at the traffic that an application generates and what happens when the traffic is delayed or doesn't come back as expected, what has to be injected into the network to make the application think that everything is still working correctly and help it tolerate some delay. So we end up with what we call an application profile lattice. So traffic comes into this, IP traffic comes in at the top and is sorted based on various criteria. And this is configurable, so it could be based on the protocol numbers, or it could be based on some more sophisticated deep packet inspection where you categorize the traffic into kind of the traditional traffic types, and then it can be further broken down out to specific protocols and applications if needed. And because this is configurable, it can be done based on the particular network that we support. So initially we've been looking at this for the Marine Corps. We're affiliated with the Navy, so the Marine Corps is a logical customer, and they have closed networks. We're not talking about internet traffic, and they have very specific applications that they want to run. So their lattice would be more simple. They don't have to support a few applications. But there's some basic requirements that the lattice be complete. There has to be a defined path, even if that is dropping the packet at some point. That has to be defined. And you can't have ambiguous or conflicting instructions within the lattice. So currently that is up to the user to configure to make sure that's all true. But we're working on having some verification and validation built into the system so that we'll avoid at least basic errors. So a couple of the use cases that we've been looking at so far for this. One is the Marine Corps scenario where they have vehicles in the field they don't have pre-established infrastructure all over the place, and so they need to communicate multi-hop. They may have a subset of vehicles that have a satellite link or some sort of infrastructure connection, but most of them do not. And they also have people on the ground with only line of sight radios that this is all communicating amongst. Another scenario is with the aerial vehicle test networks out at Edwards Air Force Base and White Sands, where they can have fades due to either the attitude of the aircraft or features on the ground or what have you. And that's a very highly mobile scenario because the speed at which the vehicles travel. So, a few minutes. So a little bit about our implementation in the standalone box. We took the AMD Zoocate platform, which is essentially their competition to the Intel Atom. I think the I/O performance is a little bit better, but use solid-state storage and put 5 gigabit Ethernet interfaces on this, and the box can run on total power and consumes about 35 watts, so it's suitable to put in a vehicle and drive around with no fan. We're running a version of Linux on this that's optimized for routing, provides us with OSPF or REP or BGP, whatever IP functionality we need to, so we don't have to build the real layer, we focus on the DTN side of things and provide that software. Okay, so in the preliminary testing, basically we were able to saturate all of the interfaces on this box with very minimal load. So performance is a non-issue even with a relatively low power box. And the future direction for this is smartphones and handheld devices. So we are concerned about the processing and I/O overhead that we require with this sort of architecture. Have a comparison there to the Cisco box, which Marine Corps was trying out for similar usage, and basically it cost 20 times more and did a fifth of the throughput of our box. So where are we now? So we presented this overall architecture, and this was kind of the first generation that we discussed in this paper. And we realized that it was useful, but it was somewhat limited in a way because IP and DTN were both incorporated in the core of the functionality. So what we're in the process of now is actually redesigning it to be more modular, so that instead of only working with DTN, it could be working with other versions of TCP. For example, if you're not concerned with store and forward so much, but just want to use TCP Westwood or TCP Peach or skips, that could be a module. And likewise, with the other side of things, maybe you're don't care so much about IP traffic, but it's a customized sensor network, or it's an underwater network, or something like that. So we're in the process of refactoring the code and making it completely modular, so that any of the pieces can be changed out for something different. And we have this deployed in a test bed and have also done some field testing on vehicles with it. And we're also looking at the different DTN bundling protocol agent options, since they have
How long of a delay is possible? A day or a minute?
So you can configure the DTN protocols to essentially indefinite, as long as they have storage, right? They'll start throwing stuff out when they run out of storage. And we've got a 0.5 terabyte of storage on these boxes, so you can store things for a long time. So the real question is, how long is it still useful information? That's going to be application specific. So that's where the application adapting comes into play. You're going to set a timeout on that particular bundle and say, this is good for the next half hour, it's good for the next 4 hours, and so forth.
Quiet crowd. Don't forget to sign that thing.
I did that first.
Yeah, good thinking.